Okay, so again, nice to see you all this week. Looks like everyone here at least got the memo that we're starting at 3 o'clock. 3
Well,
p.m. I tried to figure out everything, but so didn't Lindsay sent, like she updated the calendar link. If you haven't seen it on the Slack page to update, it should automatically tell you when it's going to be mornings, evenings, or morning, afternoon meetings. So check on that. Another item is we have another SimPEG seminar tomorrow at 2 o'clock in the afternoon. Another one of Jacques' students, Shalom, one of your colleagues there is going to be presenting tomorrow. So we'll have another good talk by them. I know they're always, I love that they're using SimPEG so much, and it's really nice to see them using it. Nice to see other people using SimPEG instead of just our own stuff. Other than that, so another thing is, so we have one new person here from that. I don't think many of us we've kind of interacted on Slack, but Neil, do you want to give a little quick introduction of who you are?
Yeah. So I'm part of the kind of extended family. Did my went with university and with Peter Fulliger, who was Doug's first PhD student. So that's how that's the connection. And Thibaut is apparently the last, so it sort of bookends in a strange kind of way. And yeah, so I work for Anglo American in their exploration division with Jamin Crystal, who's another member of the family. So it's all very, very incestuous. Yeah, so I've just been working for there, but I only started with them recently, and previously I was with BHP in exploration as well. So it's, but I've been using SimPEG for years. Actually, the first project was for Peter, actually. So he's a diehard Fortran guy, and he's like, oh, this new fancy SimPEG stuff. I'm not gonna be bothered to learn that. So you go learn it and do the things for me. And so that's how I first interacted with it, and I've been using it ever since. And it's a fantastic project, and it's really quite exceptional.
Cool. Well, we're excited to have you here. It's nice to finally meet you.
Yeah, definitely.
If not, have you been able to? Do you know who most of us are? Like, kind of watching around. Like, you looked at some of the videos.
Yeah, I do. Just by internet lurking, really. That's how you get to know people these days, right? Just Google, and an email/name.
Cool. Well, we're happy to have you here. Nice to see your face. So maybe we'll get some more people from around the globe coming too. Reach out to some of those.
Yeah, I think there's a few. There's definitely users over here. So so it'll be good.
That'll be good. Again, add yourself. So we'll go into some quick reports. Generally, we just kind of say what we've been up to recently with SimPEG. Kind of just what we've been doing. I'll go first. I put my name on there. So see, this past week, I was able to do a bunch of, like, I don't know, I just had a bunch of things that I could do, a bunch of things that just came together. So we finally got the discretized documentation together onto there. I'm not sure if you guys have played around with it yet, clicked on it, gone searching for anything in there yet. Has anyone actually used them yet? No. Okay. Well, still, like, hopefully there.
I'm no doubt there's like legions of people that aren't on this call that have. I've spent no amount of time digging around documentation, so it's always highly valuable.
Did you look at the new one?
Not yet, but I'm sure people have.
Okay. Well, I hope it's at least more. We all hope that it's more explicit with what's going on there. But yeah, it's in. The other thing is I finally pushed to do that. Our implementation, the Python wrapper for Paradiso's, MKL's Paradiso is on there. I pushed it. It's been distributed on Conda Forge now, so you can get it through there. And then I also updated PyMat solver to look for that specific for that one instead of the old PyMKL version. So that should fix up the issues with the MKL version not being correct. The easiest way to get it will be to use Conda Forge to install PyMat solver. It should pull in all the versions all the correct linkages of everything. Let me know if it doesn't, obviously, but it's all tested against them on a different version, but it should just work. Yeah, so that's up there. What else? Oh, I got the code working again. I think it seems like it's working again for SimPEG now. It just needed to, I needed to like refresh the integration with GitHub. I think it just like lost its authorization for some reason, but got that in there. Where else was I? Okay, yeah, with SimPEG, I merged in I updated the testing scripts on Devin on that branch that you had there. I just updated them there and then pulled them in to depend on the new PyMat solver, and all the tests, the SimPEG tests all pass with it. So that's good with the updated version. Also merged in a few of those small little bug fixes for SimPEG, and I'll tag a patch release either later today or early tomorrow morning, and that should fix a few of those issues that we've been having with people related to the version of scikit-learn that was installed, as well as just a few other little bug fixes. So next I'll be working, I'm working on the cross gradient review, but getting back to that. And then obviously after that, I'll finish up MT2D, EM1D. Another quick report, one of my older papers went through the process, finally got accepted. It was about a year in review, I think, through geophysics. So, yep, so that's
It's brutal. Like,
What's the title?
Oh, it's just like it's related to combining gravity and gravity gradiometry data at the same time, like just kind of laying out some basic fundamentals of like this is how you actually should do it. Just comparing how their their misfits change as a function of like if you weight them, how does that actual function change the result, comparing it. It's pretty simple, but it's more in depth and it analyzes it more. But anyway, I'll put up a preprint somewhere. And then other thing is I was playing around last week and I did a very, very simple rotated gradient implementation using the discretize operators instead of building them up individually. So the gradient regularization, I just instead represented it as I used the face inner product matrices to represent it instead of building them up individually and computing that like that. So it's just those face inner product matrices already know how to handle anisotropic parameters. So it was a natural way to include it in to get like anisotropic regularization essentially. And it seemed to work. I put in a little quick example there. Oh, one of them went away. Of like the rotated gradient. Thought that one of the other images was in there too, but it vanished. So I'll put it in the notes. You can see like it just uses a simple. It uses discretize to build the cell gradients, and then the rotated inner product matrix has the rotated information, and then it regularizes it that way, which also led me to look through the regularization functions that we have already, and comparing the simple versus the Tikhonov one. Dom, I know you were looking at it. I haven't had a chance to get back into to see what you have been changed with it so far. But as far as from what I looked at it as a first order thing, the only differences that I saw between the simple smooth and like the Tikhonov smooth regularizers is that it just had a better choice or a different default choice for alpha, like the alpha parameters. That's the only functionally different thing.
No, the gradients are different, right? The one would use stencils and one use the reg mesh cell difference. The operators are different, I believe.
the way that I was looking through it, it turned out to, it looks like it's the same.
Yeah. Anyway,
Like,
yeah,
just
that's
still-
why we have to combine them.
Yeah. Like the length, the way that the length scales were implemented in it before, like the simple one, you still divided by like the cell widths. So you had the cell stencil, cell difference stencil, and then you divide by cell widths in the simple one. So that's the gradient. That's the cell gradient right there, right? And then it just scaled.
Normalizing or not. Yeah.
Yeah, it was just scaled by like the minimum cell width. That's the only difference that I could see between those two.
Yeah. Okay. Yeah, that makes sense. That's about right. Yeah. If you look at that PR, you'll see there, like it's much simpler. And I think we just need to be able to overload what the functions are going to be on the sub objectives, right? So in your case, you could probably just overload what you want that function to be. If it's instead of being just a straight up gradient, then it could be like any function that you're computing. Anyway, that's cool. Glad to hear.
That was kind of fun. So that's what I was up to this past week. Thibaut, I see you on here.
Yeah, so like as a very small item, it just like maybe just like I just put a PR in, but like, there is like a slight discussion to have is that I'm working right now with Falcon data, and I've worked with them before, and in those, so it's a great airborne gravity gradiometry system, and they measure a very specific data for that survey, which is called GUV, which is kind of like, it's a combination of several components of the gravity gradiometry matrix. And so what we do in SimPEG is that when it was implemented with Dom and Devon, is that we actually put the option to invert for GUV, that the GUV component directly, like and the UBC code doesn't do that. Like the UBC gravity gradiometry code doesn't allow to invert for UV, but the UBC format is still a very convenient way of exporting and importing data. And so what that small PR is doing is just adding that UV component in the import and export utils of gravity data. So you export it in a UBC format, even though it's not going to be readable by the UBC code because it doesn't take that component, but still within SimPEG that works pretty well. So for me, it's just a convenient way rather than having to like export a NumPy array and like reattributing the data coordinate and uncertainty and so on, or create a pickle. It's just like there is a text file that everybody is comfortable with. So if anyone has a big complaint about that, tell me. Otherwise, I'm all for that we add that in the possibility of export and import, even if so it's just for within SimPEG.
Yeah,
Good.
I think
Okay.
fine.
That's the only trick. It's like it's a UBC export, but without having the UBC code to be able to read it. And otherwise, this point is more for Dom. I've pushed this morning like a branch where I've like cleaned up all of the like different PGI with and without cell weights. I did that quickly. I will just look at maybe there is a test that I deleted something that I should not have, like a line or something, but like the code has been cleaned up. So I think that you can jump in on that. And I've chosen to do that on a different branch because I know that, for example, Mike that's on the call right now is using the PGI branch for his inversion right now. And as long as we have not made the whole of the change with your change, yeah, it's gonna break things because like we're gonna either don't account the volume or account it twice. So it's on a different branch. I created the PR, but I realized that you're working on your branch on Mira, so maybe I can just remove that PR and you can just pull that branch into yours or something, just because it's not a PR that I can merge into main right now, or I will need to, maybe I need to create that PR on your fork in the Mira GeoSci.xyz fork of GitHub.
I'm confused. Like you want to merge this onto main, right? You talking about 1053 that you open today?
Yes. So yeah, I just created that to make it visible, but it's actually not the right way I would, because like I need your change in that PR to make it like full. It's not
What change do you
like
need?
your change, or like is the refactor of regularization at 1040. Is that not the one where you're dealing with all the standardization of cell weights and etc.?
Oh, no, it's 1038 should be merged before yours.
1038.
And I'll
Okay.
just hold up. I'll wait for it to be fully merged before carrying on my work with the refactor reg. Once you're all merged in, it's going to be easier, right? So 1038 should go in first. That's just to standardize the cell volumes in the current state of regularization. Then we merge yours 1053, and then we'll go on from there.
The 1037 looks
Okay.
good to go for you.
I'm sorry, come again?
Like 1037 was good to go for you.
Yeah, it's good on my side. At least it does what we were hoping.
Okay.
Maybe another review from you would be good. And then that will basically set the stage for yours, Thibaut.
Okay, so I might actually merge like the 1038 into that branch and make sure that all the tests are passing.
Good idea.
And
Yeah.
So like just merge your thing, and then with this one will be ready to go.
Perfect. Thanks for cleaning up. How many lines of code are you killing with this?
Like 1,000.
Nice, very nice.
Well, there is like the code, but there was like, I mean, as there were duplicated functions, there was duplicated test as well. So like actually the test was the biggest portion of like where I could remove a lot of things. So right now, yeah, it's just like the cell volumes are in no matter what, basically. So it expects that your weights, like the external weights, are weighted by, like, are designed for that.
Good. I think it's just a little bit clearer. It's a little bit easier. Just like assume one thing. Like we have a function. We're not assume it's not volume. Doesn't have a volume term on it. Go from there. Yeah, I'll double check that. I'll merge it in. Maybe tonight. Maybe today. I'll just do a quick check here. Push it in. Okay.
So that's it. That's it for me.
Cool. Devin, I see you on here next. You're muted.
Yeah.
There you go.
Yeah, so you guys have seen some small PRs. The one for a truncation factor for sensitivity weights. Then that little bug in the DCIP input output. And yeah, I had a simple one for regularization, but it sounds like everyone's work is just going to be part of this regularization refactor. And then an option for not storing all the factorizations for 3D frequency domain EM. So I haven't actually looked at the branches to see if things have been merged or if there's any improvements that have to be made. They're kind of just little one-line changes anyway. But I'd like to get those in whenever I can. Took a little look at starting the SimPEG API docs. So we're finally done with the discretized one. Good job, Joe. And so I've done some work, merged master into what I had already, and I'll just start the process for getting the SimPEG API, which I think is going to be really useful. I've actually done my first local build of the Validations Jupyter book. So I guess for those of you who aren't aware, I have a bunch of Jupyter notebooks, and the idea was to validate SimPEG against analytic solutions and against UBC GIF or any other coding packages. And so we want to see, is it accurate, or how long does it take, or can I run this problem on my laptop? And so I've done forward modeling and inversion for the potential fields codes for DC and IP 3D, and done some validations for forward modeling with octree meshes and the frequency domain, time domain EM. So it's actually quite extensive, and the Jupyter book will let you take all these notebooks and then build them and turn them into a website. So I have that done locally, and want to make that available sometime in the near future.
Any idea? Can you share what it looks like at this point, or do you feel like sharing it?
Yeah, sure. Just give me the powers and I will show you.
Go right ahead.
So this is kind of the title page it builds. I've made some fun little pictures. So yeah, we want to compare SimPEG against analytic solutions or some other packages. And so you would, right now, you would just sort by whatever method you'd like to look at. In this case, maybe you want like frequency domain EM. I've got a fun little schematic. Tried to make some fun schematics for that. And the four validations I have right now, I've got a conductive 1D layered Earth. I've got one where it's also susceptible, and I've done the sphere in a vacuum example. So you would go and click on one of these, and you would have the comparison. It would show you some things about the geometry, and then would give you a comparison. So in this case, I had like an X, a Y, and a Z magnetic dipole, and I predicted the X, Y, and Z component of the response. So 3x3 grid, and compared the analytic solution, the SimPEG octree, E3D version 1 and E3D version 2. And so I've done this with, yeah, quite a few things at this point. So there's even a magnetics inversion, sparse norm inversion for a block and a half space, and you can click to see the actual script that was used to construct this. And yeah, in this case, I was able to recover it using sparse norms with each code. But yeah, we really wanted to kind of use this as a way to not only verify if the codes are working properly, but also to think about which one is working best, and if those if the superior code can be used to improve the other one. So that's one of the things I've been working on. Does anyone have any questions about this?
No, that's great, man. Hey, can you go back to the curves? Why are we not seeing they're like exactly banging on top of each other? Sorry, the analytic solution versus yeah. Come back one more.
Oh, the frequency domain EM?
Yeah. So why are we not seeing
some of these are null coupled, so the analytic solution is completely zero, and then the numeric solution is just very, very, very small.
it's like exactly the same answer between E3D and SimPEG? Is that why we're not seeing the red and the blue curve?
Yeah, that's exactly it.
Huh.
Those codes are matching so well.
Cool.
Yeah, it gets a little bit different, I think, when we have susceptibility. Oh, sorry, my mistake. The numerical codes are really quite consistent, but there's a little bit of a discrepancy between the analytic solution and the numerical solution in this case.
Oh, that's
Doing this
surprising.
stuff is really God's work, 100%. Like it's. I know it's like at the end of the day, it's just establishing what we all hope to be true, but it's nice to trust but check. So this is awesome.
Yeah, I'm hoping it'll come in handy. And I guess the idea is we don't really want to maintain them, but we've talked about the idea of rerunning it once a month or something to see if nothing breaks. Yeah, and I'm happy with some of these images that I made. Joe, you may want to use this for 350 to show the directions of currents.
Yeah, I think I might steal some of these images when I do the what is EM type slide. They're great.
But Dev, that seems a bit surprising that because like all SimPEG UBC code has basically same bias, like, because when you look at sometimes they don't match with the analytics. And yeah, it's a bit surprising that they kind of, I was just like thinking about the random worlds, like I was thinking, oh, some matches, some doesn't match. But the numerical codes are actually almost same. That seems a bit suspicious. I'm not sure.
But they're not quite the same. And we've learned a bunch of this by doing this validation. So with the potential fields, it turns out that the UBC GIF codes will actually recognize locations that are above nodes and above edges, and will actually remove the terms that would cancel out. Whereas in SimPEG, when you had kind of like 0 divided by 0 minus 0 divided by 0, there was a stabilization constant that was added. So they're not the same code. And for the DCIP, for instance, we have a code with SimPEG where one of the formulations will project to the nearest cell center, or there'll be an interpolation to the nodes, I believe. And in UBC GIF, there is a fictitious source kind of a thing, a sort of a fictitious source created to make the right-hand side. So you have kind of an analytic solution for the potentials in your domain, apply the operator to construct the right-hand side. And so you're kind of solving for the anomalous contribution that way. So they're not the same code. And when you go and look in the details, you find these things out. So, and I made sure that I modeled these with identical meshes to make sure that that wasn't the reason why things were different. So there are some fundamental differences in some of these coding packages.
Yeah, absolutely. It was just specific to what kind of Dom was asking, because I think there were like those images about the
EM,
yeah, EM comparison that looks quite suspicious on my end. Just looking at that, yeah, like those plots. The black is the analytic, and all the other is numerics. Yeah, the fact that
they're banging on top of each other, it's pretty crazy.
Yes, that's a bit kind of suspicious.
So I would imagine that these are like these frequency domain ones are probably the ones that are closest in implementation between UBC GIF and SimPEG.
Yeah.
So
yeah, I would think so as well.
And also knowing that they're both using like Paradiso to solve it on the back end too. Like these are probably the closest possible things that are
same mesh, same solver.
So it doesn't
yeah,
really
the one I mentioned about DCIP, actually, let me just I've got a bunch of pole dipole lines, and if I compare I've got kind of a percent error, and the discrepancy between the SimPEG Octree DC resistivity forward model and the equivalent using UBC GIF codes is a relative error of about 4%.
Okay.
So, and this can be explained by the fact that if you have no topography, using the analytics solution and then creating your right-hand side with that is really, really good. But if you have topography, that's not necessarily the best choice, whereas SimPEG will actually approximate the right-hand side. It will go and do an integrated source term and do all that business. So the way that the right-hand side is constructed in both codes is fundamentally different, and that explains why it's 4% off.
Sure. That's great. Well, 4% seems like the limit that I would assign for the uncertainty. So having the 4% error seems okay. John is nodding, so we're good to go, maybe.
Yeah, and it depends on how finely you discretized. I think there's like 5 cells between each electrode. I didn't go too crazy small, but I went fairly small to show that I could be very accurate if I discretized finely there. Yeah, so that's been a fun little project. And in talking with somebody yesterday, Colton at Colorado School of Mines, he was talking about trying to simulate some time domain EM stuff. And I think he wasn't really able to, I think he just wanted to simulate something with a VTEM waveform, and he wanted to actually create the source loop, and he wanted to measure dB dt. And he tried to find different ways of using it, an EB formulation or an HJ, and he just couldn't get what he was trying to do. So it seems like you can't use the line current source class with every single simulation class for EM problems. There's kind of just some work to be done to allow you to use any source class, any receiver class, and those all the simulation options for the EM codes. So that's something I've considered starting some work on. Haven't really done any of that yet. I know Lindsay started, but it would be very useful at this point.
Yeah, before you do that, Dev, I guess for the inductive source, you would rather consider just using, there's an analytic solution for a path, like for magnetic potential. So you would like kind of do the same trick. So you derive like a magnetic potential for a path. Then you basically sum that over. I think I could send you like some of the Julia code that Eldad wrote. I think we can just transfer that into SimPEG. That's probably better rather than using the existing line current, because that doesn't really make sure the magnetic field is divergence free.
Yeah, so that was my understanding too, is if you wanted to have a frequency dependent or time dependent galvanic source, you may choose to just use a line current. But then if you wanted to ensure that it was divergence free and it was an inductive source, you would use the magnetic vector potential. And then wouldn't you also take like a numeric curl so that it's divergence free numerically?
Well, I think if you start with the magnetic vector potential, then yeah, it should be divergence free, I guess, at least for the source term. So
yeah, or are you talking about changing the right hand side when you're solving for electric fields, or are you talking about using a formulation in terms of potentials?
No, I'm like we can just use the same formulation, but just deriving the magnetic field from the vector potential. So that's how we're typically doing for either magnetic dipole and circular loop. So we
okay, you input it as a magnetic source term instead of an electrical source.
Yeah.
Okay. Yeah. Any advice on that would be super useful. I'm kind of keen on learning those details a bit better.
I'd have to check and see. I know Lindsay had started working on something she has like a line current for an HJ formulation, but
yeah, and I talked to her yesterday because I know she had started it based on conversations our group had several months ago. So yeah, there's members of the community that want to be able to do things that they're not necessarily able to do right now, and there could be some improvements.
Yeah.
And we've also noticed some differences between the UBC and the SimPEG codes for how things are done, and look for the best one, and yeah, that kind of stuff. What else? Oh, I was going to ask Sagi what the status of the EM1D branch is, whether or not that got finalized as a project and we can put it away, or whether or not there were still things you wanted to do there.
I have lots of things that I wanted to do there, but I think it's actually in good shape. I think the tests are all passing. The missing point is the tutorials. So the great tutorials that you generate, Dev, it's not not up to date anymore. So
yeah, they all break. It's fine.
We need to update that. I think that's it. I think other things are all working. So
Right.
Okay. So I could do that. I could put some time into updating the tutorials so that they work with what the package or what EM1D is doing.
Yeah, I think it's one of the things that's still on my radar. It's where we have like the normal 1D simulations working, and they seem to be working well. Like you said, all the test passing. There's just still parts of the EM1D that will need to get migrated in. We've talked about it before, the the stitched regularization.
so yeah, I think that's all like a sort of done as a draft, and it's
Yeah.
sort of like I can replicate what I used to do. So it's in a working mode, but yeah, we probably need to update to be kind of similar to the current feel of the SimPEG structure, I guess.
Yeah.
So is this something that can go into this regularization refactor project? Or is this something that we want as a regularization aspect to do it as part of the 1D project?
I think it should be separated from that because we could use it in other.
Yeah. This one is much simpler. I think I was basically like inheriting the sparse regularization for this. So I think later we can readily switch it to whatever the latest regularization, I guess. And I think it should be separate.
Okay. Yeah, just let me know what I can do to speed up the process, because it'd be nice to get that in.
Yeah, so that, I think speaking of that, if you could just like finalize that tutorial part, I think then we can merge the current version into main and leave whatever that we need to further develop as the kind of future items. I guess that's
so we should cut out like all the extra stuff that's randomly around in that branch right now, and then merge the finalized parts in, because it is pretty well finalized, those individual things.
Okay. That's basically it for me. I think we already talked about some of the aspects of regularization, but I dropped a little picture of the results of doing an identical UBC and a SimPEG DC resistivity inversion. So there's still some differences, even if it's the same mesh, and I used the same kind of truncation on the sensitivity weights. Yeah, I think maybe SimPEG is updating the sensitivity weights at each beta, but I kind of noticed that the general shape of what's returned is much different between SimPEG and DCIP Octree, and I'm kind of curious as to why that is.
Interesting. So that's that image you have in the notes there.
Yeah, it kind of, for whatever reason, the SimPEG one of all the stuff that I've tried kind of wants to like bleed out down and to the outside. And I did kind of notice that it was putting stuff in places when the cell size increased. And I did make sure that I was no longer using Tikhonov regularization. I switched to simple. And it's better, it's a lot better, but it's not quite where I was expecting it to be.
Mm. It's interesting. Let me check something really quick here.
You see the issue on a DCIP Octree with the Octree change. They have that line happening there.
But it's also like if you see further down on the SimPEG one, like the SimPEG one like better handles that line, right? But then it also like pushes stuff even below it where it changes again at something later.
Yeah, but you know, for the sensitivity weights to work great, you need to hit the perfect perfect state where you fit the data just enough, right? If you go a little bit too far, then you're gonna start seeing the sensitivities again.
Yeah.
And in this case,
Yeah.
the volumes are kicking in.
Yeah, and I tried to be careful, and I tried to see how far along the convergence curve it was, because I believe that the target misfit in SimPEG and the target misfit in UBC GIF, there's like a subtle difference between those. So, and also with SimPEG, you kind of start your initial beta based on this eigenvalue thing. So you can't really hard code your cooling schedule in the same way that you tend to do with UBC GIF codes. So I kind of tried to consider that and make it stop at roughly the same place, but that could be a bit of an explanation.
I'm going to show something really quick here.
Sure.
I think it's, so when I was doing the rotated gradient things, I was of course comparing it to the original like simple regularization. So what I did here was with a tensor or a tree mesh.
Mm-hmm.
So it kind of looks like this. I just made a tree mesh that looked like this. So my model was like a syncline, like zoomed in, it's in here. So this was just with simple regularization and the like I wasn't doing anything super special. Like I was updating sensitivity weighting and using that simpler regularization that we have right now on the tree mesh. And it was like I noticed that similar kind of thing too. Like it started doing this, right? Like you can see where the cells, like even further out, right? When I replaced it, so I switched it to do that new kind of regularization. So this is what is, it's like this with my minimum cell width. So it should have scaled them correctly the same way as it should have, as it was before, but this should have accounted for that difference in scaling between doing it with the mass cell gradient mass matrix as opposed to the smooth derivatives or the simple smooth. And I still have it updating the sensitivity weights the similar way, but I ended up with something that looked like this instead. So just like it seems like it should be similar. Like I think I have the weights look all the same, but I don't see like.
Can you scroll back up, Joe? Just scroll back up your iterations. I'm just curious. Oh yeah, and you're finishing almost at the same place. Yeah.
Yeah. So before it was slightly higher, but it's about the same place. At 4.13, 2.9, it's about the same regularization rate.
What is the new regularization that's different from simple, Joe?
So in simple, from what I looked at it does this. Essentially, and then alpha X, alpha Y, alpha Z are essentially set to the minimum cell width in each of those directions. So it was square, my minimum cell sizes were square, so it's easy to just say that, oh yeah, alpha X is, so the alpha is 14. Actually, this alpha X is the minimum cell width squared. So that's why it's the minimum cell width was 4, and I put a 16 out front. This new one is doing it like this. So it's taking the gradient and then it's building this this mass matrix from the using the discretized operator for the faces.
Isn't it same? Because if the MF is just diagonal term, then isn't it same with the new and
that's what I was under the impression. I thought it was going to be pretty close. My goal is to at least get it very similar to each other. but I noticed that it was also not, I didn't see that kind of like. So
Okay,
it's still different.
Joe, can you just evaluate both reg with a random vector, the same random vector, and then they should give you exact same answer, right? If they don't, then you know that they're, you know.
Well, I know they're different. Like I've done it before. Like I know they're different values.
Oh, they're way different.
Yeah, but they're constructed very similar to each other, which is why I thought it was odd. Like fundamentally, they're constructed very similar to each other, or at least thinking about it. But
Isn't it like a is it that's like related to that stencil stuff? Because there's a slight difference.
yeah,
Uh,
I have to go back and check, but I think it is related to that stencil. I just think Discretize combines this, is probably slightly better at building this than just using those stencils and the average matrix piece. At least that would be my guess.
Yeah, that since you're getting such different values, it's just the alphas are not the same. You might be over smoothing in your case than in the other case, right?
Possibly.
It looks, I mean, it doesn't look like an octree discretization issue. It looks more like we're regularizing definitely the model, right? It's smoother than the other one.
Yeah, I know it. Well, it almost is in this area.
Well, we don't really see the octree change. I mean, it's a good thing, right?
Yeah, not in that area, but like we do see it further out, which is what Devin was showing in that other image. Like it's you
Right.
saw it further out, right? As opposed to.
That's the problem. That's the problem I've been having trying to sell it within the company here, the Octree, is it's the bigger cells down. That's the ones that really pop out. You get to see that.
So it didn't seem like it really changed much in this. It might be regularizing a little bit more, but anyway, that's just something I saw from this really quick as well when I was noticing it. Anyway. I think it just handles the interface changes slightly differently.
Joe, were you using the face diff in Octree? Is that what you were using here?
Cell gradient.
Oh, okay. So then
I guess the cell gradient operator, so it's built off of the
then
face.
it seems like equivalent, but yeah, okay. I don't know.
It should be about the same, right? Like it should. But I'll have to dig into it a little bit deeper to see why it's actually being different. Anyway. At least it seems like a nice way to incorporate rotated gradients into that L2 regularizer.
Yeah, and the same thing we talked, right? The only thing that we would need to be able to do is to split those into orthogonal components instead of being just one big block, to be able to split it into for having the directionality, right? Say like this is like one direction and then two others. Because then we still have the old knobs to be able to push things in one direction versus the other. Otherwise, it's just one big.
Oh yeah, here, I'll show you what I did. Sorry. I'll show you how I implemented it really quick. So I built that matrix like that. Anisotropic regularization by doing that. Like I had a principal alpha direction or principal alpha components. So I was smoothing in alpha 1 more than 0.1, and then I defined the rotation. I defined the angle of that alpha 1. And then I had that, essentially this is like that diagonal matrix at each location. And then this is the rotation matrix that does it. And then it puts it all together like this. So you would be able to, like in each cell, you'd be able to give it like a, your sigma 1, sigma 2, or alpha 1, alpha 2, and then its direction. It looked pretty neat. I thought it was interesting. We'll have to play with it a little bit more, Dom, and figure out what's exactly going on different there. But... Well, I think we probably had a long meeting today. It's been a while since we had a long meeting. Anything else anyone wants to share?
I did the reviews for you, Devin, right? So you can have a look at the comments and then we can carry on Git.
Sounds good.
Awesome. Talk to you guys later. I gotta step out.
Okay.
See ya.
I think it's a, if anyone else, kind of good, call it a good meeting.
Have a good one, everyone.
Yeah.
Thanks everyone. Thanks Neil for
Bye.
joining.
Bye.